Hey everyone, my name is David Hull, and today I will be discussing lab number 5 for Physics 2211. For mine, I did a rolling object. Before we dive in, here's a quick intro describing what the lab was. The purpose of my lab was to observe and compare an object's position traveling at a constant velocity with its predicted position produced by a computational model. My lab will record a marker at a constant velocity, calculate its position using the software tracker, and then compare it with my computational model made on GlowScript. This data will then be used to demonstrate the principles of Newton's second law. And then last thing before we get started, it will be important to define the systems versus the surroundings. In this case, the system is the marker, while the surroundings are everything else, the air, table, etc. Newton's second law, this states that force equals mass times acceleration. It can also be stated as the net force is equal to the change in momentum of a system over the change in time. Then we can rewrite this equation so that the final momentum equals initial plus the net force times time, understanding that momentum equals mass times velocity. We can then produce the velocity update formula located at the bottom of the screen. This formula proves that when the net force of an object is 0, its velocity does not change. Yeah. Moving on to the procedure. I first recorded a video of the marker rolling at a constant speed across a flat surface. Once the video was recorded, I placed the video into Tracker and then found the ball's position frame by frame over set time periods. And after this, I graphed the data and also put it into Excel. Then I went into GlowScript and created a computational model of the marker's predicted position. Once I had both graphs, I compared them and made conclusions about the lab. Here is a video of our marker. Hope you enjoy it. Nice, there it goes. Okay. All right, Tracker. In Tracker, I selected the center of mass of the marker at each frame and the graph of the position versus time. Once I exported the data to Excel, appears to be linear. The total time the marker rolled was about 1.9 seconds, and the initial position was negative 0.0035. Using the first 2 points, I found the initial velocity to be 0.592 meters per second in the x direction. And then these 3 data points will be used in the computational model. GlowScript. Looking at the computational model, there are a few important things to note. First, we set the net force vector equal to 0, since we know there should be no net force with a constant velocity. Next, I entered the initial position, velocity, and total time that I mentioned on the previous slide. You can also see the velocity and position formulas used under the apply the momentum principle section. A few things to note: mass doesn't matter here since Fnet is 0. We're assuming friction and air resistance are also negligible, and since the velocity is constant, our position time graph should be positive. Now that we have both graphs, we can compare the two. The two slopes are very close, as you can see, and the observed data becomes slightly slower than the predicted towards the end, you can see that it tails off, the blue line right there. This is because the predicted model doesn't take the surroundings into account. Surroundings like friction and air resistance, that's why it's more of a linear path, whereas the observed tails off. I started to mention this on the previous slide, but here are the errors that could have affected the data. First is friction and air resistance. These are the surroundings, as we mentioned towards the start of the slide. The table and air molecules slow it down. Grounding errors are also common in any experiment, so those need to be accounted for. But a very likely error for any inconsistencies is the position tracking in the tracker data. Lastly, here are some questions to consider after the lab. What would happen if the marker had acceleration? Technically, there is a force acting on it by the table and air, but for the sake of this lab and the computational model, we would have to set Fnet equal to ma and solve it out from there. Then also we can consider what would happen in this lab if we used a heavier object, like a bowling ball, for example. This wouldn't change anything since Fnet equals 0. The mass has no effect. If anything, using something like a bowling ball would lead to better results since it would be or it would experience less friction if we consider the contact forces. Thank you all for listening, and have a great day.